Hey everyone, let's take a look at number 12 in section 6.3. We're going to find the volume of the solid obtained by rotating the region B in the figure shown below about x equal 9. So this figure is basically the same one that's used for several problems in this section. There's two regions, regions A, which is sort of this region up here, and region B that I've shaded in. So I'm going to focus just on this one. And it's got this generic y is x squared plus b, and then here's the value of a down here, and these numbers will vary. Your problem probably doesn't have exactly these same numbers, but for mine it was b was 6 and a was 9. So this is x equal 9 here. B again is equal to 6. And notice, of course, the quadratic function is x squared plus 6. And when x is equal to 9, what's the y value? Well, plugging in 9 gives me 87. So that's the height there. So we're going to rotate this about x equal 9. And x equal 9 will correspond to this vertical line here. And so we're going to rotate about that line there. When you look at this region, if we're going to do the disk washer method from this section, we're going to have to use integrate with respect to y and use horizontal rectangles. And the problem is this region is not horizontally simple. It is vertically simple. It's not horizontally simple. And that's because for values less than or values of y between 0 and 6, remember b is equal to 6 here. So we'll just say this is equal to 6, right? For between y equals 0 and 6, the left endpoint is always the y-axis, which is corresponding, of course, to x equals 0. And the right endpoint is always this line here, which is x equal 9. In fact, the length of any rectangle will always be 9. But then something changes between at y equals 6. So between y equals 6 and y equals 87, now our region has the left end of our rectangles on this curve, y equals x squared plus 6, right? B is 6. And then the right endpoint is on x equal 9. So basically what we're going to have to do is divide it into two integrals if we want to use the disk washer method. And so I'm going to talk about this region here from y equals 0 to y equals 6. Okay, so let's take a look at that from y equals 0 to y equals 6. As I integrate there, an arbitrary rectangle would be like right here. Okay, and notice if I take that rectangle and rotate it about the line x equal 9 and back into the paper and all the way around, we're going to get a solid disk. We're going to get a solid disk. And the radius we're rotating from the axis of rotation, x equal 9. So from x equal 9 all the way to this end, this whole length here is the value of r. Right? That's the value of r, the radius of our disk. And that between y equals 0 and y equals 6, that r is always equal to 9, right? Because we're x equal 9 here, x equals 0 here. And so our radius is 9. And the area is just pi r squared, so pi times 9 squared. So we're going to integrate that from 0 to 6 for the first region there that that we're going to generate the solid of. And then between y equals 6 and y equal 87, what's happening? Well, now I look at an arbitrary rectangle. Notice those rectangles are going to go from a width, if you will, of 9 units all the way down to 0, right? As we vary from y equals 6 to y equal 87. But when I rotate this back into the page over here, we're going to get this again disk, right? A circular disk. And the radius is just again the length of this rectangle, the x length of that rectangle. So how are we going to proceed? So I've got this same situation, pi r squared. So what's the value of r? Well, I need to know the x length. So I know that this side is x equal 9. All right, that's the line we're rotating about. What's this line? Well, it's y equals x squared plus 6. But I need to know what is the x length. So I need to solve this for x, right? So I do that by subtracting 6 from both sides. And I swap sides there. And then I take the square root, and I'm going to take only the positive root because, again, we are in the first quadrant. Both x and y are positive. And so the length of this, the x length of this, uh, is going to be given by what? It's going to be x equal 9 minus x equal what? X equal the square root of y minus 6, right? Because that's the boundaries for this rectangle, right? On the right, it's x equal 9. On the left, it's x equal the square root of y minus 6. So the value of r is 9 minus the square root of y minus 6. And notice that's going to work here because when y is 6, again, our length of our rectangle, excuse me, our length of our rectangle should be 9. So plug in y equals 6 here, and what do we get? This becomes 0, and I get 9. But then notice as y gets bigger, I'm going to be subtracting stuff from 9, making the radius smaller and smaller and smaller, getting closer and closer to what? 0. In fact, by the time I get to y equals 87, I should have 0 for my uh, the radius r for my circular discs, right? So if I plug in 87, what do I get? 87 minus 6 is 81. What's the square root of 81? That's 9. 9 minus 9 is 0. So it's going to work. So I integrate pi r squared, where r is 9, from 0 to 6. That's what I've done here, integrating from 0 to 6. I pulled the pi outside. R is 9, so that's 9 squared, 81. I can even pull the 81 outside because it's a constant multiple. And then from 6 to 87, I'm going to integrate pi times this r all squared. So I've got to do a little work there. And so I want to clean this up by squaring this out. First times first gives me 81. The inner and outer are negative 9 times the square root of y minus 6. So that's negative 18 times the square root of y minus 6, or y minus 6 to the 1/2 power, plus last times last is negative times negative positive. The square root of y minus 6 squared is y minus 6. So just simplifying, 81 minus 6 is 75, plus the y minus the 18, y minus 6 to the 1/2. So this right here is what I'm going to integrate from 6 to 87. So let's do this one first. It's easy. What's the antiderivative of 81? Well, it's just 81y. Don't forget the pi there. So I got 81 pi times y is the antiderivative. I can pull this 81 out, and I am basically integrating 1. And upper limit 6, lower limit 0. Over here, antiderivative 75 is 75y. Antiderivative y is 1/2 y squared. And the antiderivative of 18, y minus 6 to the 1/2, I did over here. Simple u substitution. U is y minus 6, du is dy. So I got 18 u to the 1/2 power. And antiderivative is 18 times 2/3 u to the 3/2 power. And then 3 goes into 18 6 times. 6 times 2 is 12. U is y minus 6. So there's the antiderivative, 12 y minus 6 to the 3/2 power. Of course, it's minus there. So I'm going to evaluate that at 87. Don't forget the pi out here. And evaluate it as 6 and subtract. So I went ahead and did that. I mean, you can use your calculator to help with that computation. When here was mine. Of course, this one's easy. Plug in 6. I get this. Plug in 0. I get 0. Over here, pi, first plug in 87, 75 times 87, 1/2, 87 squared, 12 times, well, 87 minus 6 is 81. And 81 to the 3/2 power, that's the square root of 81, which is 9, and then cubing it gives me 729. So that's all in parentheses minus, right, evaluation at 6. So at 6, it's 75 times y, which is 6, plus 1/2. 6 squared would be 36. Half of 36 is 18. And then if I plug in 6 here, notice 6 minus 6 is 0, so that's going to go to 0. Okay, so just finishing it out, we will have 75 times 87 is 6,525. 1/2 of 87 squared is 7,569 halves. 12 times 729 is that. Minus, well, 75 times 6 plus 18 is 468. And then using your calculator, you can compute this to 2,187 halves. So all that work, this is 2,187 halves pi plus 486 pi gives me, if you add those two together, you get 3,159 halves pi. So a lot of fun with some arithmetic there, but use your calculator to help with that calculation. You do have to understand what it means for the 3/2 power and such. Okay, so I hope this is helpful on this one.